Hi everybody, welcome to another ICD DWF repair video. I have bought this device on eBay quite cheaply if we exclude the outrageous shipping cost of nowadays. This is an Enertec 7151 computing multimeter. It is actually made by Solartron, but rebranded as Enertec for the French market in the 1980s. All the functions can be selected by this keypad. It has both front or rear inputs, the usual sockets for banana jacks. Let's quickly have a look at the rear panel too. The rear inputs actually are not the same as the front ones. For instance, there is no input for current measurement, but there are the additional inputs to make 4-wise resistance measurements. This instrument has the IEEE 488 interface that was the most common interfacing option in those years. But it can also be interfaced via the RS-232 serial interface, which was a less common option on those test instruments. However, the RS-232 signals are available on a rather unusual DB15 connector that is shared with quite a few other different interfacing options. Of course, this multimeter was sold as not working, and of course I verified that both the user and the service manuals are available for download before deciding to buy it. Links to the manuals are in this video description. This was a rather unusual multimeter, as it could do automatic computations on the measured data, even cascading 2 or more different programs, storing the raw or computed values in the internal memory. It even has an internal CMOS real-time clock IC to take measurements at regular intervals, starting at a configurable delay even of several days. Oh, and by the way, it uses not one, but 2 8-bit CPUs. The disassembly procedure is described in the service manual, so I won't show it here. However, the multimeter has been already opened, and by a careless person for sure, since only 2 of the 4 case screws are present. This already gave me a bad feeling. The second obvious thing I've noticed is that the naked battery that is needed for the backup power of internal real-time clock and data storage static RAM when the unit is powered off has already been removed because it was leaking. However, it seems that nothing has been done to restore the oxidized traces and pads. So, in order to work on the bottom PCB where the battery was mounted, I've removed the 2 screws that hold this PCB to the bottom half of the case. These screws are passing through the power transformer laminations, and luckily were both present. I've also noticed that the firmware EEPROM had no label, but only a sticky substance over the window. The other EEPROM holding the firmware for the other CPU was in an identical state, so I cleaned both EEPROMs and applied labels on them, since I wanted to dump them and save their content anyway. The damage caused by the battery leakage seems not too widespread, fortunately. So I started sanding off the crusty residues, just to expose the copper on pads and traces, avoiding removing the copper too if it's not already gone. Then the larger traces and pads can be restored by simply retining them. When the trace is too small and the connection is lost, I have inserted a small wire on the nearest via and soldered the wire to the trace on both sides of the PCB. If a trace is too damaged, I have simply bridged it with an insulated wire on the other side of the PCB. So it is time for the first power on. Well, so far so good, it doesn't show any error. But it seems only showing meaningless values. And on all functions too. Well, seems like I have to find some other faults. After I powered it off, I happened to pass one hand near the power transformer, and it was so hot that I couldn't leave a finger on it really. Now, this multimeter doesn't have any fuse on the transformer secondaries, which is a bad choice. I then started looking for any short circuit on the various secondaries. And here we are. This is the plus 12 regulator input on PCB 2. Totally shorted to ground. Luckily, there are only 3 components on the shorted node. The first component is a bridge rectifier that makes both a positive and a negative rail from a center-tapped secondary. This can be tested in circuit and appears to be good, despite having supplied current into a short circuit for who knows how much time. The second component is a little voltage regulator, an LM78L12. To test it, I would need to lift one pin of it. And the third component is a 40-volt aluminum electrolytic capacitor. Also for this one, I will need to lift one pin of it to see if it's the one shorted. I think, however, I will start with this capacitor as the most likely one. So I've desoldered one end of the cap. And yes, it's indeed shorted. The LCR meter shows 185 milliohms, a pretty good short circuit. I think it's the first time that I find a bad Philips capacitor in all these years. Anyway, I've substituted it with a radial electrolytic mounted vertically, that's still lower than the power transformer. Another thing I wanted to check is why the fuse on the transformer primary didn't open. The label says we need 100 mA slow blow fuses for the 240 volt primary. Well, both fuses were 160 mA slow blow, so I've substituted them with the correct ones, but I'm not going to try if they blow with one shorted secondary. However, that didn't change anything. The multimeter acts still in a crazy way. I think that the plus 12 rail is only used by the RS232 lever converter. However, now the power transformer only gets barely warm after a few minutes. So I started to follow some troubleshooting steps from the service manual, but I could not really find anything wrong. All of a sudden, however, I realized that there was something really missing. I'm not hearing at all any relay clicking. A multimeter like this has quite a few read relays, like we can see in this part of the schematic, also because it can be fully operated by remote interface control. We should hear some relay clicking both during power on and whenever we switch to a different function. I then searched on the schematic how the relays are toggled, and it appears that all of them are switched on and off via IC13, which is a very common Darlington array. Most of the inputs to IC13 come directly from one CPU. So I got back to the bench to see the actual signals around IC13. But wait a moment. There is no IC13 installed here. Someone pulled it out of the PCB. The good news is that a missing IC13 is a very good reason for not hearing any relay click. I've then decided to examine all the analog PCB to check for more missing parts, and indeed I found a few more of them. That's the bad news. A missing capacitor and a trimmer capacitor here. Another missing capacitor. and another missing one here. In the end, I found all these missing parts. The two diodes were kind of hidden next to a relay. Most of them can be easily replaced with parts I have in my spare collection, but for example I could not find any data about that coated relay part number. I can only assume it has a 15 volts coil. Or maybe it's just a 12 volt relay like this other one. I'm only sure it's a single pole, normally open contact reed relay. Another problematic part might be the Teflon trimmer capacitor. For sure that will cost a good fraction of what I've already paid for this multimeter. At this point I was really unsure whether or not I would try to fix it or abandon this project. I have stopped working on this project for a few days. Then I thought I would first assess the extension of the damage. As you can see in this image, all the missing parts are in the SC front end circuit. Maybe because this multimeter developed a fault on the SC ranges. So, if I just replace the relay driver IC, I should be able to test the DC and resistance measurement functions at least. If they appear working reasonably, I can then decide to try to restore also the SC front end. Then I've soldered a socket and installed a new ULN 2003 integrated circuit. Let's see what happens. Yeah, the sweet reed relay sounds. The DC millivolts go almost to zero when shorting the leads. That is good. Also the resistance almost goes to zero. So far so good. Let me measure a random 9-volt battery. With reversed probes, it is almost the same value. That's fine. Now I'm trying a random 2.7 kΩ resistor and it's surely in the correct ballpark. Even the DC current function seems working. I'm not interested in actual calibration at the moment. Now I'll try to replace all the missing parts on the AC front end. I'll try to adapt parts I already have in my spares collection, since I have no idea if there are other hidden faults and if I will ever be able to make a reasonable calibration of this multimeter. I'll start with the missing relay whose part number gave no useful results on a web search. Some other relays on this instrument have for sure a 12-volt coil. They are driven with a small resistor in series to the coil to drop a few volts, since they instead used a 15-volt supply rail. However, the relay I have to substitute has no dropping resistor on the coil, so I assume it had a 15-volt coil. I found a similar sized reed relay in my collection. This one has a 12-volt coil, and I'll add the dropping resistor right on one leg, since I also have to add some wires on all other legs to make it fit properly on the intended PCB space. And here it is after soldering it on the PCB. Then I found a Teflon trimmer capacitor with the right value range, but with the wrong PCB sides. However, since one mounting pad was already stripped off by whoever removed the original capacitor, I've soldered it on the nearest wire. The replacement for the fixed capacitors posed no special problems. Here is the ceramic one. This is a 5% polystyrene foil capacitor, which is a superior replacement for the original polyester foil capacitor. This capacitor is instead one exact replacement. I've then decided for the moment to not replace the two missing diodes, since it seems they are only needed as a protection in case of overvoltage at the inputs. I'm going to see if the AC measurement came back to life, then decide what to do with them. I'm going to measure the output of an AC transformer that should be around 10 volts. Well, looks reasonable. And this is the mains voltage at the moment. It also looks reasonable. Now I need to replace the two clamping diodes. Their job is to start conducting whenever the voltage on the common node is greater than plus 11 volts or lower than minus 11 volts plus 1 year drop in both cases, of course. However, they aren't just regular diodes, but they need to be low leakage ones, because when the voltage is between the two clamp values, they must pass the least possible leakage current. The diodes they have originally used have, in fact, very low leakage currents. Now, these diodes can still be ordered at very reasonable prices, but I thought I'd try another option. This is a figure from The Art of Electronics 3rd edition. It's about leakage on diodes, and as you can see, the 1N3595 that we used in the Solartron multimeter is a very low leakage diode, having about 0.01 picoamperes of leakage current at 0.1 millivolts of forward drop. However, we notice that, for example, the base to collector junction of a very common 2N3904 transistor is about 10 times better, and the base to emitter junction of the same transistor is about 200 times better. However, the base to emitter junction of almost any bipolar transistor cannot withstand any reverse voltage higher than about 5 volts, so for our 11 volts clamp application I'm going to use the base to collector junction. So I soldered both 2N3905 base to collector in place of the original diodes, after cutting out the emitter legs. I've also added a piece of heat shrink on one leg of the leftmost transistor to avoid the leg touching a nearby wire. I have measured again the same AC transformer and then the mains voltage, but this time the mains voltage was quite higher than before. At this point I've also noticed that the LCD display was getting a bit flaky with the PCB movements, so I thought it was time to refresh the solder joints on the display PCB connectors. Another thing I wanted to address is also the extreme darkness of this LCD backlight. This is with room lights turned off. Since I was going to disassemble the display harness, I thought to try using some random white LEDs in place of the original ones. So I first tried substituting only one. I think you can tell the difference between the new one and the old ones. This is the end result. Unfortunately, I've left some dirt between the plastic cover and the LCD display. At this point, to discover if there are other hidden faults with this multimeter, or even to be able to use it regularly, I should attempt a complete calibration. Unfortunately, I don't have any calibration source stable enough for such a multimeter. However, I could try to calibrate it against my HP 3456A multimeter, which has been very stable in these years, and anyway, it's really all I can do. However, part of the calibration procedure of this multimeter is carried over the IEEE 488 interface, or GPIB, so I need to verify that the interface is working fine first. To interface the instrument to a PC, I'm going to use the simple GPIB to USB converter that I built years ago, following a project on a web page that's linked in the description. This always worked very well. So everything is connected. I've set the instrument to address 26. Let's try to change the mode. It threw an error. Okay, it worked this time. Notice the display has the RAM indication now. So it seems the interface is working fine in both directions. That's what I wanted to check. At this point, I can attempt a calibration procedure of this instrument, but that will be shown in a future video. I hope this was an interesting journey into such an instrument. If you have any question, please use the comment section below. This is all for today. Have a nice time and thank you for watching.